Hello everybody, we're going to do part 2 of our periodic trends presentation today. Remember that we split it into 2 parts because it is a pretty long lesson, so it's a little bit easier if we split it over 2 days. Couple of reminders, there is a lot of notes. This is a lot more words than a normal chemistry lecture. We like our math, we like our drawings, our diagrams, our graphs, so this is a little bit more words than normal. Please don't try to write down every single word. What I want you to do is focus on listening, focus on understanding. Remember, you can always add to your notes at home. The PowerPoint and the video is always accessible to you online. Capture enough in your notes during class so that you're paying attention, that you kind of have the main talking points, and then leave space, come back, add, and annotate later on. Remember, don't overthink this stuff. Try not to elaborate and keep talking yourself into a wrong answer. Realize we only have a certain number of trends and we're going to practice them until we're really, really good at them. And don't stress about the exceptions. Remember, there's so many things that break our patterns, but what we are learning in this class is about the patterns and understanding those. Okay? So, first trend for today is going to be electronegativity. Electronegativity is a measure of the ability of an atom in a chemical compound to attract electrons from another atom in the compound. What we're measuring is basically how hard is one atom pulling on the electrons, trying to hog them. When we say that they're sharing an electron, sharing is not always equal. When my 2 kids are sharing a toy, chances are they're not taking equal sharing turns, right? Somebody's always hogging the toy more than someone else. So a similar thing is going to happen here. So the thing with the higher electronegativity is the atom that is pulling on the electrons harder inside the bond. Electronegativity increases as we go up, increases as we go to the right. I like to be lazy and draw a big diagonal line. Really, really careful here. Noble gas column is the lowest. Why would they want to attract an electron? They already have a stable electron configuration. They're already happy and stable. They don't want one, okay? So you need to be careful that when you're drawing your arrows that you do not include the noble gases. You should point your arrow towards francium. Do not point it into the noble gas column. Always make sure you understand that here the noble gases are the lowest. Ionization energy, they're the highest, but electronegativity, they're the lowest. So here's our electronegative atom, and it's pulling harder on the electrons. So let's look at why it decreases going downwards. That's because the electrons are further from the nucleus. They're in those higher energy levels. Okay, well, that's like a 1-point answer. To get the rest of your points, you need to explain that because there's increased shielding, you're not going to really have as hard of a tug between the nucleus and the valence electrons. And because that attraction is not as strong, it's going to allow the electrons to be pulled away from the atom a little bit easier. Okay? Increasing to the right, we have a smaller radius. We have our increased effective nuclear charge, which means the nucleus is pulling harder on those valence electrons. And so, because we're looking at those outside valence electrons for our bonding, if the nucleus is pulling really hard on them, right, we're going to be able to pull them in closer, and that's going to be a higher electronegativity. So once again, you can see shielding is our explanation for up and down, and effective nuclear charge is our explanation for left to right. Make sure that you do not just say, increase shielding, increase great effective nuclear charge. Don't just say that, okay? Make sure you're explaining it. I don't want to see you just spitting a vocab term at me. You could, in theory, get full points for an answer that does not use the word shielding and does not use the phrase effective nuclear charge. You cannot get a full answer if all you say is shielding and effective nuclear charge. So you need to be a little bit careful. The vocab words make it easier to give our answers, but if all you're giving is a vocab word, that's not a good answer. All right, reactivity. Reactivity is a measure of how things behave and how violently the magnitude, the size of their reactions, okay? If they have a very small reaction and they just kind of bubble a little bit, that's a low reactivity. If they explode and there's flames and things, that's a huge reactivity. The thing that's interesting about the pattern on the periodic table is it's going to be opposite for metals and non-metals. So you have to be a little bit careful. Metals increase their reactivity as they go down and get bigger. Non-metals increase their reactivity as they get smaller going up. Okay? You have to be careful. Once again, be mindful of your noble gases. The noble gases are inert. They are not reactive. They do not want to react. They already have a stable electron configuration. Metals increase going down because if you think about it, metals are trying to get rid of electrons. So being a larger atom is advantageous to them. It's better for them to be larger because it's going to result in the lower ionization energy, meaning it's easier to take an electron away. The easier the reaction is, the more reactivity you have. So your larger radius, your increased shielding results in a lower ionization energy, so it's easier to get those electrons off, resulting in a big reaction. Non-metals, however, are the opposite. They want to gain electrons, don't they? They are trying to get the electrons stolen, yanked off of another atom. So they need a really high electronegativity because they need to be pulling on somebody else's electrons. And so the smaller the atom, the greater the effective nuclear charge is, right? The smaller that radius, the harder the nucleus can pull. So your smaller radius, your greater effective nuclear charge, that gets you a higher electronegativity, and then you can attract an electron more easily. You may sometimes see people talking about electron affinity. That is a very similar trend to electronegativity. They have the same pattern. Electron affinity is measuring kind of how much more stable is it once it's finished, okay? So don't stress out about it too much. I do like to throw the term out at you because you may stumble across it. As long as you rank things in the exact same pattern as electronegativity, you'll get the correct answer, okay? It increases in the same directions as electronegativity. So, to summarize, I like to look at the chart, okay? So this should be one of your printouts. As you go down, you get an increased radius, increased shielding. As you go up, you have an increased ionization energy, an increased electronegativity, also that increased electron affinity that you might see once in a while, okay? As you go to the right, you're going to get a larger ionization, larger electronegativity, larger electron affinity, greater effective nuclear charge. As you go to the left, you get a bigger radius, okay? I love this graph. This is the one that I personally, if I'm going to imagine it, this is the one that I use. However, some people really like this one. I do like this one because it gives you some examples. Okay, if we're looking at the periodic table, kind of the top left quadrant up towards lithium, okay, has a small effective nuclear charge and a small diameter. Down towards the bottom left, towards cesium, you have a really small ZeV and you have a very big atom. So it's very weak forces there. You don't have much electronegativity or affinity. You have a very, very low ionization energy and you got a really big radius. Kind of the top right quadrant up near fluorine, okay, you have huge attractive forces happening. You have a really strong nucleus, that really strong ZeV. You have a very tiny atom, so it can pull really hard. So you get very high, strong electronegativity and affinity. You get a very high ionization energy, and you get that very small radius. And kind of the bottom quadrant, you get this intermediate force again, right? Where this time you have a very large ZeV, you have a strong nucleus, but your diameter is pretty big. So kind of looking kitty corner here, top left, bottom right, small ZeV, weak nucleus, but it is small diameter, which is, good. Down here, you got that nice strong nucleus, but it's a really big atom. So those end up kind of somewhere in that intermediate range. Top right, very strong forces. Bottom left, very weak forces. Okay. This does take a lot of practice. One of the things that's going to be helpful is that we will be ranking these atoms. I'll give you 3 or 4, and we'll put them in order from small to big radius, or we'll put them in order from small to big ionization. And once we start ranking them, and I ask you, well, why did you put that one first? You'll start to naturally use the explanations of shielding and effective charge and the attractive forces and the diameter. You'll start using those terms to kind of explain your answers of ranking. And when you start doing that, it really starts to cement in your brain. Okay, there are 2 kind of fun videos to watch. The first is called Brainiac. It's a British TV show that's really silly. They're kind of goofy people. It's a very classic video to show for the concept of reactivity of metals. One of the teachers at our school hates this video because it turns out they kind of augmented one of the reactions. They made it bigger than it would be in normal life. I personally feel like as long as you know that, and you understand that it was trying to be really memorable, I think it's okay to show it to you. I'm not lying, right? I'm telling you that it's been augmented, but because it's so memorable, I think it will help it stick in your brain. And then the second video is an old black and white video from World War II. And they used sodium to make bombs. And after the war, what are they going to do with all this leftover sodium? And so the video is going to show you how they disposed of it. And the way they disposed of it is nothing we're allowed to do anymore these days. So I think it's kind of fun to show. And it's also a pretty memorable video. I found this link on YouTube that has a quick summary of the stuff, and it does explain some of the exceptions to the trends. So if you're the kind of person that likes to know the exceptions and you find that interesting and it helps your thought process, some people find that if they can learn the exceptions to the patterns, it helps them remember the pattern better, then please feel free to watch this on your own time. It's not something I'm going to show because it is a little bit outside the scope of the class. At this point in the lessons, we will do a worksheet where we look at some of the exceptions and try to figure out what they might be, but I'm not going to do a formal lecture on it. But if it is something that interests you on your own time, you can watch that video. Okay. At the end of the PowerPoint, if you open the PowerPoint, you can find a couple of slides about electron affinity. So if that's something that interests you also, if you want to go learn about the affinity a little bit more, you can look at those slides that are at the end of the PDF PowerPoint. I'm just not going to do them in the video because we're not going to be teaching that this year. Okay? All right, everybody, that's it for part 2. And then, focus on your practice. Ask me questions. I will explain it over and over and over if you ask. I don't mind, right? You just got to ask. So I hope that was helpful, and that's it for the second part. Bye, everybody.